right, any questions?
Yeah.
Tuesday.
That's a good question.
When's the test?
Yeah.
Tuesday.
I'm finishing chapter 19 today,
Good.
and so it would be a week. That's our standard date, yeah, next Tuesday.
Today.
Okay, so for the test, we've all taken it, right? So it's okay
No.
to discuss it? No.
Unfortunately, we
Can't discuss
haven't all taken it.
it. No.
Wait, who has
Can I
taken
just-
it?
I can't
Some
discuss it.
person had it.
Am I not allowed to say anything about it?
That could be
No.
Chris.
Yeah, let's not talk about it right now. Yeah,
Nobody wants to talk.
because there's a penalty associated with, but you have to have some kind of valid reason to take it. That's what happened. So I can't talk. I'm sorry, I can't talk about it right now.
Sore subject anyway.
I can talk about the next step.
All right,
Okay.
let's do that.
I'll need to post the practice test.
Wait, I have a question concerning the final. So you said that chapter 25 will be part of the final. How much of a portion is going to be a part of the final? Like a significant, or just like
No.
just to include as an equal amount in every other chapter?
Right, except maybe a few extra questions.
Okay.
The final exam is going to be a lot of multiple choice.
A lot.
Something like about 60 multiple choice. And so that's like anywhere from 5 to 10 questions per chapter.
Okay.
And so a chapter that I didn't cover, like chapter 25, would see maybe 10 questions. But it's not going to be like 1/4 of the test is chapter 25 and 3/4 is everything else.
Got it. It's more like 10% is only chapter 25.
You're right, or less.
Got it.
How do most people usually perform on the final? Is it like a
Worse,
good grade?
worse
or-
than their average grade or better
Yeah.
than their average grade? Just
I mean, does it help?
Korean advice.
So, first,
Do curve it? Yeah.
I have to be careful what I say because I think what I've said in the past is people interpreted it wrongly.
Didn't study.
And didn't study as hard. And so I've seen people do much worse on the final exam than on the regular test. And I don't understand why, because they're getting this grade all throughout the semester, and then all of a sudden the final.
They choked.
But you know, a few people, yeah. But last year I saw a lot of people that their final exam actually dropped them a grade rather than help them.
People do worse.
And the thing I say about the final is that with 60 questions, can I ask you anything really advanced?
No.
No, and so you want to stick to the basics. The questions, you have to average like 2 minutes a question or less, and so that means a lot of questions you should be able to rapidly answer, and some that require calculations, well, you can take more than 2 minutes, but not much more than 2 minutes, right? And so it's not, if I made it calculation intensive, it would be a very long test. And so in the past I've said, you know, stick to the basics, you know, basic concepts, basic calculations, review your past multiple choice questions that you've encountered. But I think what people did was they just thought, well, it's going to be basic, so I don't really need to study as much. So talking to some people who grade suffered because of the finals, they said that they didn't study or prepare.
Considering the possible calculations, will we be given a table of the equation, like we did last time?
Yeah,
Okay.
right.
Got it.
For the final exam, you don't have to have the equations memorized.
All the constants will be given.
All the constants and the equations, at least the major equations will be
Yeah.
given. You might have to use
Like
a,
PB and RT, but then
Yeah.
might have to like rearrange it.
you might have to rearrange it. Usually I give PB equals nRT. You know, the stress of the final, people don't want to even think about PB equals nRT.
Oh boy.
You'll have the entire 3 hours. So it's mostly multiple choice, and then you have some equation writing problems, like predicting the products.
Using elementary process.
No.
No?
Predicting the products of a reaction using the stuff we talked about in the first week. You know, you haven't, you know, the quizzes,
Yes.
except that, you aren't going to have everybody to have. You'll have to do it on your own, that kind of thing. Huh?
And then on the homework, you said that are you going to take out the chemical reactions handout, the overview that we're supposed to do in like the beginning of the semester?
Yeah.
That could be like get canceled, I guess.
No.
Someone asked for it.
The chem equations homework
Yeah.
is still due.
Oh,
Oh.
Mhm.
when's
When?
it due?
At the end of the semester.
Oh, good. Okay.
All right.
Yeah, like
Chemical
reaction.
You know, like the overview that we got before the class started?
Yeah, the chemical reactions sheet. We did it maybe the first week. We looked at. Yeah. It's been a while. You know, if Spartan, I'll tell you what I was going to do if Spartan wasn't working on all the computers. If Spartan wasn't working on the computers, I was going to do the chemical reactions homework sheet as the lab. But since it was working, we didn't. That's good. Start preparing for the final. One of the things you want to do is just go back to the beginning of the class and just, you know, under low pressure, just flip through stuff we covered earlier. Hopefully you'll find it. Oh, that stuff like the chapter 15 stuff. Oh, that's not so bad. We'll see. Chapter 16 calculation.
Yeah, like crazy ice.
Yeah. Hopefully those won't be so bad. But now's the time to find out if you need to do a lot more review or not. All right, other questions?
You?
No. Tomorrow we're going to start chapter 20 in lab. Chapter 20 is, deals with electrochem. Our lab is electrochem, so I'm going to lecture and lab together. That is, we're going to talk about batteries and then we're going to build a battery.
Like on the computer
No,
or actual?
actual no.
Oh, quick question. When's the lab due again? Is it due tomorrow or
No, the
Thursday?
formal
Yeah.
lab write-up, Thursday.
Okay.
Just turn in what you have done. That's the synthesis lab.
And still
Yeah.
grouping, right?
It's a group thing. Turn one lab per group. If your partner dropped out, you can join another group if you want, or you can just turn it in. There are a lot of people who are turning in individual paper. They just found it easier. You're welcome to do that too. You don't have to work in a group if you prefer to do it by yourself.
Get it before, because I did get a better
Seriously, I want to bring a steak next time.
All right. Anything else? Where did we leave off with thermal last time? Did we do the boiling of water?
Like calculating the entropy from that?
Yeah.
Like the delta S thing, right?
Yeah,
Delta
it-
S degree final of water gas minus by like the water as a liquid. I think we got the equation.
Last thing we were talking about was like the entropy of the system, good and bad, and when the spontaneous reactions occur.
All right.
when they don't
All
occur.
right. That's it. So we're talking about delta G.
Yeah.
This is what law of thermodynamics?
First law? Or no, second law?
Yeah.
Second law. Second law.
Second law of thermodynamics. Second law of thermodynamics says that for all spontaneous processes, what's observed is an increase in the entropy of the universe. And so we can see that here because delta G is the new state function called the Gibbs free energy, the change in the Gibbs free energy, and it's equal to minus T delta F. And so the sign is just switched. And so what we're looking for is different scenarios. Did we talk about this? If this are plus?
Yes.
Okay. But, one of these terms is energy. So what we want to do is we want this to be negative. And so we want to minimize energy. We talked about that? Minimize energy, maximize entropy. Yeah? So how is minimizing energy related to the entropy of the universe? So this is the whole point of the earlier discussion. How is minimizing energy related to increasing entropy of the universe? Well, we know from the first law of thermodynamics that energy content of the universe is constant, it's fixed. So if something loses energy, something else might change. So when we look at the universe as a whole, nothing really changed in terms of the energy, right? Except something did change in terms of the entropy. Right? And so how is this delta H being negative related to an increase in the entropy of the universe? It's because we talked about the entropy of energy. Right? Not all energy forms have the same entropy. For example, heat, is that a high entropy or a low entropy? It's a high entropy, whereas chemical potential energy would be a lower entropy form. And so here, when the reaction is typically exothermic, we're converting the chemical potential energy into heat. So even though energy is fixed, it's constant because the surrounding is gaining just as much energy as the system lost, the entropy is actually increasing in that case. Well, anyway, this is what we're looking for. So typically we just think minimize energy, maximize entropy. And did we look at water yet? So let's do an example here where we look at a reaction. H2O liquid goes to H2O gas. Our basic calculation is going to be a delta G. And since our data is from Appendix D, this is going to be delta G, little superscript of 0. The superscript of 0 means what? Standard conditions. And what are standard conditions? You really have to drill this into your head because it's easy to confuse. Standard conditions is not STP because this standard means that, we're at 1 bar or atmosphere pressure and concentrations are 1 molar. Temperature is not part of thermodynamic standard conditions. However, it is part of gas, STP for gases, 0 degrees C. The reason why we do this is because the data that we have in Appendix D is all under standard conditions. The pressures are this. Actually, in Appendix D, the pressure is 1 bar, the concentration is 1 molar. And so when we do a delta G calculation using Appendix D, there are 2 ways to calculate it. One way is it's the sum of the delta G's of formation of the products. Since it's under standard conditions, we have to keep these under standard conditions too. Delta G's of formation of the reactants. So this is a Hess's law application. This is the easiest way to calculate delta G. And so if we calculate it, we just look, what are the products? Well, we have 1 mole of H2O gas, and then we look for delta G of formation of H2O gas. And so we just go to Appendix D, take a look at that data here. H2O gas has a delta G of formation, which would be the second number here, of minus 228.6 kilojoules per mole. Minus 228.6 kilojoules per mole. And so the moles cancel out. Energy is an extensive property. And so the more you burn or the more you make, the more energy is going to be required for that particular process. So that's the product. Then we look at the reactant, which is H2O liquid. So minus, we're forming this from 1 mole of H2O liquid. And then we look at the delta G of formation of H2O liquid, which is, this is delta H of formation. The next one is delta G of formation, which is minus 237.1. So minus 237.1 kilojoules per mole. Moles cancel. So that gives us delta G of 8.5 kilojoules positive. Is that right? Positive 8.5 kilojoules. That's the easiest. There's another way of getting delta G, except, even though there's no standard temperature, the temperature for this is fixed. How is the temperature fixed? The temperature is fixed because of the data table. Rather than publishing a whole bunch of different temperatures, which would generate a huge volume of numbers, they just pick a temperature. So what's the most convenient temperature to pick?
Room temperature.
Room temperature. And what is room temperature?
25 degrees Celsius.
Yeah, or 298 Kelvin. So this is going to be at 298 Kelvin. All these are at 298 Kelvin. And so this is the delta G naught that we just calculated at 298 Kelvin. If we had data at other temperatures, we could figure out the delta G naught at those specific temperatures as well, but we don't. And so, there's another way to get delta G naught at 298 Kelvin, and that's by using the other equation here. The other way we can generate delta G naught at 298 Kelvin is delta G naught is equal to delta H naught minus T delta S naught. And so we'd have to calculate delta H naught. What's the easiest way to calculate delta H naught? By using Hess's law and the formation. So delta H naught would be the sum of nu times the delta H formation of the products minus the sum of nu delta H of formation of the reactants. And these data are under standard conditions, and these data are also at 290 Kelvin. That's what the data table is. So this is delta H naught at 290 Kelvin, which is fine. And so how much product? We have 1 mole of H2O gas times the delta H of formation of H2O gas. The delta H of formation of H2O gas is minus 241.8 kilojoules per mole, minus 241.8 kilojoules per mole. The moles cancel. Okay, minus the reactant, so H2O liquid, it's minus 285.8. So we have 1 mole of H2O liquid, and the delta H of formation of H2O liquid is minus 285.8 kilojoules per mole. The moles cancel out, and we get a delta H of plus 44.0. kilojoules. All right, if we have a delta H of plus 44.0 kilojoules, that's not helping this, right? It's not favorable. It's endothermic. And so let's see what our delta S is. Now, our delta S is a little different because delta S is going to be rather than the enthalpies of formation or the delta G's of formation, these Gibbs free energies of formation, we're looking at the absolute entropies. And so here we have 1 mole, and entropies depend on the amount because the more moles you have, the greater the entropy should be. And so we have 1 mole of H2O gas, which is the product. And so this is the entropy of the products minus the entropy of the reactants. Now I'm going to forgo the nu and the sum. It says products minus reactant. So 1 mole of H2O gas, what's the entropy of H2O gas? Go to the table, entropy of H2O gas is 188.8 joules per Kelvin mole. 188.8 joules per mole Kelvin. The moles cancel. Okay, minus the reactants. Well, I have 1 mole of reactant, which is H2O liquid. And the entropy of H2O liquid is 69.91 joules per mole Kelvin. The moles cancel again. And this gives us an entropy of 118. What does this come out to? 117? 0.89. Okay, the units here will be joules per Kelvin. And so now we have our delta S, and that looks favorable. Our delta H is unfavorable, our delta S is favorable. But right now, our delta H is dominant. Our delta H is the dominant factor because here, the overall, it should be plus 8.5. And so let's go ahead and plug those numbers in here into our equation. I'm going to leave this up for comparison. Our delta H came out to plus 44.0 kilojoules. Our T is 298 Kelvin, so data. Our delta S, I'm going to convert that into kilojoules, 0.11889 kilojoules per Kelvin. And so the Kelvins cancel, that leaves us with units of kilojoules. So the first thing I'm going to do is do this term, plus 44.0 kilojoules. And can somebody punch this out? 298 times 0.11889. $35.42 kilojoules. And so you can see here, this is positive 44, this is negative 35. It's not enough to cancel it out. And so the whole thing is going to be positive, which is unfavorable. And so what does it come out to? You want to punch out the number. $858? 8.58 kilojoules. These two numbers are supposed to be the same. But this one comes out to 8.6, this one comes out to 8.5. What would you attribute that to eventually?
Round off there.
Really round off there. It should give you the same number. So which one should we use? Well, let's go ahead and use this one. All right. So we see that this is non-spontaneous. And then we could be done with that. It's just non-spontaneous at 298. But is it possible to boil water at other temperatures spontaneously? Yeah. And so what we can do is we can change delta G, because this is a scenario that we saw earlier. And the scenario is this. When delta G is equal to delta H minus T delta S, if delta H is positive and delta S is positive, then this is favorable, this is unfavorable. We can make this more favorable by increasing the temperature. The more we increase the temperature, the bigger the second term will be, and eventually it'll cancel this term out. And so if we can cancel out this, then we can actually reverse the driving force by just making it a little bit bigger. And so this we call non-spontaneous at low temperature, but it's spontaneous at high temperature. And so let's go through this. Well, what is high temperature? Let's determine that. And so the next question we're going to ask is, at what temperature will this become spontaneous? In other words, basically what we want to do is we want to go from delta G, which is positive right now, to delta G 0 to delta G negative. And so if we keep increasing the temperature, if we increase the temperature from 298, then that's going to make this term bigger. The bigger this term becomes, the less positive this sum is. And so we just got to figure out what temperature that'll cancel out. And so in other words, we want to make delta G from positive to 0 to negative. And so the borderline is at 0. So we'll say delta G is equal to 0, which is equal to delta H naught minus T delta S naught. And then we solve for temperature. The temperature is just going to equal delta H naught over delta S naught. And so plugging in our numbers here, delta H naught is 44.0 kilojoules. Delta S naught is 0.11889 kilojoules per Kelvin. And this gives us how many Kelvin?
$369.77.
369.77. Or about 370 Kelvin. So what this means is this. At 370 Kelvin, then these two terms cancel each other out. If the temperature is greater than 370 Kelvin, then it should go negative. And so we want a temperature greater than 370 Kelvin. If we have a temperature greater than 370 Kelvin, this term will dominate. It'll be bigger than the first term, which means the whole thing becomes negative and spontaneous. Well, we already know at what temperature water boils. What temperature does water boil spontaneously? 373 Kelvin. And so we're off a little bit. Why are we off a little bit?
Still round off there? No?
Is that round off error? Turns out that's not a round off error. We're off a little bit because I did something here we didn't talk about.
Something with the delta H then?
It's the temperature. Okay, it is with delta H. The problem is we need the delta H value at the temperature, 307, whatever it is. And we need the delta S value at the same temperature. But we don't have those. And so this is what we did. Let me back up just 1 second.
We use the delta H. at 25.
So it's 208, not
Right.
the reason why.
So what we did is this, you know, the temperature should be delta H naught at that temperature, delta S naught at that temperature, but we don't know what the temperature is. And so we can't look it up. And so what we're saying here is that we don't have that, delta H, we only have delta H at 298 Kelvin. And so we're saying that delta H at temperature T is approximately equal to delta H at 298 Kelvin. Delta S at temperature T is approximately equal to delta S at 298 Kelvin. And so we're making this assumption that delta H and delta S do not change much with temperature. This is an okay assumption. As long as the temperature range is limited. You know, if you get to too extreme of a temperature range, then, like for example, if you're looking at, delta H at minus 300 Kelvin, at minus 300 Kelvin, everything's going to be frozen solid, right? And so, so as long as the temperature range is limited, but limited means different things. You know, for something like nitrogen gas, you know, nitrogen gas is close to an ideal gas. You know, the temperature range is huge. For something like steam, well, steam's not such an ideal gas, and the temperature range is going to be more limited. And, you know, so you're looking for phase changes. So, okay, solution. Well, in this case, at 298 versus 370, no problem.
So does that mean whenever we do these problems, we're going to get an underestimate of what we should really have?
Well, it depends.
If the temperature's high, we're going to get a high temperature, right?
That's a good question. I'd have to think about it, think about other scenarios. I'm not sure if you can just generalize it as one. You usually just calculate it. Could be because, you know, everything's going to be boiling at a higher temperature, usually, but there are other scenarios where you're looking at decreasing the temperature to make things go. There's spontaneous at low temperature versus high temperature. So we've got to be careful. All right. So here we could use the temperature to change the driving force. In other words, even though delta H and delta S do not change with temperature, delta G changes significantly with temperature. Significantly. With temperature. In fact, in this case, this is what we kind of see visually happening, because here delta G naught is up here. Delta G naught doesn't, you know, there's no standard temperature. And so under standard conditions here, we start off with a positive delta G naught, and then we change the temperature. And the higher the temperature we go, the more negative delta G naught becomes until it hits 0. And so up here it's all positive, non-spontaneous. And then it hits 0 at 370 Kelvin. And so temperatures below 370 Kelvin, it's positive, and it becomes increasingly positive at lower and lower temperatures. But anything above 370 Kelvin, it becomes increasingly negative and spontaneous. And so we can see that delta G changes dramatically with temperature, because not only are we going from, you know, non-spontaneous to spontaneous, it's changing over the entire temperature range. And the higher the temperature we go, the more spontaneous it becomes. And so this gives us a way to alter the driving force for a reaction under standard conditions. Now, what do these delta G values mean? Have I talked about delta G and K yet? Or delta G under non-standard conditions? No? Not yet. All right, let's talk about that now. And so, ways to alter driving force. I forgot to say one way this is in the afternoon class. I'll remember to say it tomorrow. Okay, ways to alter. One is the temperature. And two, we can go non-standard. Well, what happens with non-standard conditions? Well, under non-standard conditions, we need a non-standard table. And so here we know that delta G under non-standard conditions is equal to delta H under non-standard conditions minus T delta S under non-standard conditions. And so do we have these values, these non-standard values? In other words, is there a non-standard table in addition to our standard conditions table in Appendix D? No. And the reason is there's too many variables. I mean, what is standard? Well, standard is 1 bar, but if you're non-standard, it's any pressure other than 1 bar, which is everything else. So the table would be enormous. Concentrations, what's standard concentration? 1 molar. Do we do every single reaction at 1 molar? No, not even close. And so there is none. But fortunately, what we can do is this. We can correct our delta G under standard conditions. And so this we do have, right? We have. So we apply a correction to delta G under standard conditions, which looks like this. It's delta G under standard conditions, and the corrections RT ln of Q, where R is just 8.3145 joules per mole Kelvin. T is the temperature. Q is the reaction quotient. Remember the reaction quotient from early on? The reaction quotient is just the product raised to whatever power over the reactant. And the difference between the reaction quotients and K is that these are just your given conditions. Your initial might not be at equilibrium. So standard conditions are a little bit funny. Because when you sit back and think about standard conditions, let's look at a generic reaction under standard conditions. AA plus BB, let's say this goes to GG plus HH. Under standard conditions, the standard, let's say our initial conditions, under our initial conditions, if they're standard, then let's say these are all gases or all aqueous solutions. Then their concentrations or pressures must be equal to 1 bar or 1 atmosphere or 1 molar. And so these are all 1. Under standard conditions, that has to be 1. And if they're all gases, it's 1 bar. If they're all solutions, it's all 1 molar. But one of the strange things about standard conditions is, does it say that only the reactants are 1 and 1? Or everything's at 1 and 1? It's not specific because it says everything is at 1 and 1. And so if we were to carry this reaction out under standard conditions, do you know what G has to be? 1. And H? Same. And so this is a very weird way to carry out a reaction, because the weird way is because of this. Normally if you were to react A and B, you just mix A and B together, right? But if you want to do this reaction under standard conditions, you can't do that. Because if you want to do this under standard conditions, you have to mix A and B 1 to 1, and
1 to 1.
G and H also 1 and 1. That is 1 molar or 1 atmosphere. So everything has to be 1, but it doesn't make sense because, if you're trying to make G and H, this means you have to first go out and buy it and then mix it in and then try to make it. Does that make any sense at all? No, and so it doesn't make any sense at all. And the reason it doesn't make any sense at all is because if you don't do everything this way, then we don't have an easy way to compare different reactions. Because if you say, okay, this is going to be 1 and 1 and this is going to be 0 and 0, then all of a sudden, predicting driving force for reactions becomes a lot more complicated, because that's going to change the values, because these are going to be no longer under standard conditions, these are going to be under non-standard conditions, and we need another table or many tables to figure it out. And so to get everything on one table, we have to do it this way. Does that make sense? It's the same thing with oxidation states. Oxidation states might not be the most accurate, but the only way to compare redox properties is to treat everything the same, no matter if the bond is nowhere near ionic or not, And so this is the way we do it, unfortunately. And so this is delta G under standard conditions. And we're looking, if delta G under standard, if this is equal to 0, what does that mean? That means there's no driving force at all. Delta G naught is equal to 0. Well, when delta G naught is equal to 0, that's an interesting scenario, because we'll talk about this in just a minute. That means essentially it means there's no driving force, no change, and in fact it's going to be at equilibrium. If delta G naught is less than 0, then that means we have a driving force, right? In other words, this isn't enough product. We want even more product, and we want less reactant. And so these are going to grow above 1, these are going to shrink below 1. If delta G naught is greater than 0, then we say the reverse reaction is favored. If delta G naught is greater than 0, then this is too much product, not enough reactant. We need to decrease these numbers and increase these numbers. And so this is what a delta G naught type calculation tells us. When we're starting off with these initial conditions, is it going to shift right, or is it going to shift left, or is it at equilibrium? All right, what we can do is this. When we're thinking about delta G naught equal to 0, then that means that if this is equal to 0, there's no change. There's no driving force for change. That means this initial conditions must also be the equilibrium conditions. Because the only thing that, if we have less than 0 here, it's going to be minus AX minus BX plus GX plus HX. If delta G is greater than 0, it's going to be plus AX plus BX minus GX minus HX, right? It's going to shift one way or the other, or change one way or the other. And so what we're looking at is we're looking at the equilibrium. So what is the relationship between delta G and delta G naught and K? How are these related? And so when we look at delta G is given by delta G naught, which is standard, plus this correction RT ln of Q. If there's no driving force for change, so that is delta G under non-standard conditions is equal to 0, that means nothing's going to change. It should be at equilibrium, which is equal to delta G naught plus RT ln of, well, Q is going to go to K because now we're at equilibrium. And then we end up with this equation. Delta G naught is equal to minus RT ln of K. And so here's a relationship between delta G naught and K. In other words, K is equal to e to the minus delta G naught over RT when we rearrange this equation, RT. Here. So if delta G naught is equal to 0, then you know what K is equal to? K is equal to, well, we'll just plug it in. If delta G naught is equal to 0, e to the 0th is going to be 1. So K is equal to 1. Now, does that make sense? Because now that you look, if delta G naught is equal to 0, that means this shouldn't change. This should be the equilibrium conditions. That means that K has got to be, well, K is the product over the reactants. And so it's got to be 1 to the G, 1 to the H, 1 to the A, 1 to the B. Well, 1 raised to any power is equal to 1. And so it's just going to equal 1, which means that this is already at equilibrium. Well, let's talk about this for another minute because this is kind of unusual, right? How often is delta G naught equal to 0? This is rare because how many equilibrium constants at 298 Kelvin have you seen that are 1? Not really. You know, you see 6.3 times 10 to the minus 8, 1.8 times 10 to the minus 5. But did you have any equilibrium constants that were equal to 1? Have you even seen an equilibrium constant equal to 1? No, because an equilibrium constant equal to 1 means all the concentrations or all the pressures must be 1 at equilibrium. So this is kind of perfect. I've seen 1 up there, you know, the K equal to 1. But other than that, no. What about this? A delta G equals 0. Now, a delta G not equal to 0 is different than a delta G equal to 0. A delta G equal to 0 is much more common because a delta G equal to 0 is just telling us our K, but in this case the K is not equal to 1. The K is equal to something else, a normal K. And so this is always a bit confusing, this thing, the delta G not equal to 0 or delta G equal to 0. And so let's talk a little bit more about this. And, see. So this is under standard conditions. Under non-standard conditions, we have this. We have AA plus BB yields GG plus HH. Under non-standard conditions, what are my pressures and what are my concentrations? Under non-standard conditions, they can be anything. And so here, whatever I'm given, initial, this is initial concentration of A, initial concentration of D, initial concentration of G, and initial concentration of H. This is whatever I want. And it could even be 1. If all these were 1, then I wouldn't call it non-standard, I'd just call it standard. But if they're not 1, then it's non-standard. And so here, well, look, if delta G is equal to 0, well, this is non-standard. What does that tell us? If delta G is equal to 0, then our initial concentrations, whatever those are, our initial pressures, whatever those are, must be at equilibrium, right? They must be at equilibrium. In other words, when we calculate this, remember Q calculations? If Q is equal to K, then the given conditions are the same as the equilibrium conditions. And so the system's already at equilibrium. And so this would be that kind of scenario. When delta G is equal to 0, oh yeah, these are all already the equilibrium concentrations. There's going to be no shift one way or the other, right? Here. Now, if delta G is less than 0, what does that mean? There's a driving force. And in fact, we need to form more product. If delta G is greater than 0, then the reverse driving force is present. That is, we need to form more reactants compared to our initial. And compared to this. All right, the other thing that's kind of funny about standard conditions is this. Once the reaction starts, are we still under standard conditions? Once the first little bit of A and B react, what's going to happen? All of a sudden, we're no longer going to be under standard conditions, and we're going to switch over to non-standard conditions. Now, the usefulness of this, you think, oh, well, non-standard, we need to know more non-standard. The usefulness of this is to make comparisons. And because, like in Chem 1A, when you're trying to predict a chemical reaction, do people say, well, tell me, will you have a driving force under this temperature, under this concentration, under this pressure? Did you ever make predictions like that? No, because it's too much. And so in Chem 1A, what we do is we automatically assume that the concentrations are going to be standard, the pressure is going to be standard, and then we come up with some simple rules for predicting driving forces for chemical reactions, which we reviewed at the beginning. Precipitate formation, this kind of stuff. But in Chem 1B, what we want to do is we want to open up the variables. We want to say, okay, what happens if you change this concentration, or what happens if you change this temperature? Are we still going to get a driving force? And so this is why we're going through learning these. Well, the utility of this, delta G naught under standard conditions, is so we can compare all different kinds of reactions. And if you see a delta G less than 0, what's going to happen if we do this reaction normally? Like, a normal way of doing this reaction is not starting off with product. We don't want to go out and buy product. We want to make product, right? And so we start off at 0. Well, if these two are 0, is that going to help the driving force or hurt the driving force? It's going to help it. The less product we have there, the more driving force we should. This is similar to the common ion effect we saw earlier. And so these delta G naught values are still quite handy, even though they're just at one snapshot in time. It's a good way to compare. All right, so let's take a look at another problem that we're going to do. And this would be here. Let's try to get H2O liquid to go to H2O gas at 298 Kelvin. Well, we already saw at 298 Kelvin, this isn't going to happen, right? Because at 298 Kelvin, delta G naught is greater than 0. It's non-spontaneous. But even though delta G naught is greater than 0, we can go, at 298 Kelvin, we can go non-standard. And so what we want to do is we want to take a look at delta G. Is there a way to get delta G to go to 0 or become negative at 298 Kelvin? And so, in other words, can water boil at 298 Kelvin? At room temperature. And you do a calculation to find out, and it turns out yes. The answer is yes. Now, how can we do that? Yeah, by changing it from standard conditions to non-standard conditions. And so try non-standard. And so if we go non-standard, we'll use our non-standard delta G. Our non-standard delta G is equal to our standard delta G plus some correction, RT, ln, Q. Now, our delta G under standard conditions at 298 Kelvin, this is equal to plus 8.5 kilojoules. And so what we have to do is we have to change Q so that we can cancel out this term here. Well, Q is just equal to the activity of the products, raised to some power, over the activity of the reactant, raised to some power. Now, the activity of a gas is just its partial pressure. So this is going to be the partial pressure of H2O gas raised to the first power. The activity of a liquid is just, pure liquid is 1. And so Q in this case is just equal to the partial pressure of H2O gas. So what we have to do is we have to figure out, at what Q value will we get a minus 8.5 kilojoules? Because if we have plus 8.5, we need to cancel that out with a minus 8.5. And so we look for a Q value that makes this whole thing minus 8.5. And then if we adjust the Q, we can make it bigger than minus, or more negative than minus 8.5. That's minus 8.6. When we get to minus 8.6, then this is going to go spontaneous, okay? And so at that borderline, we want to transition from a positive delta G to a negative delta G by going through 0. And so we'll set delta G equal to 0. And this is going to equal delta G naught plus RT ln of Q. Now, delta G is equal to 0. We call that equilibrium. And so this Q goes to K. And so in other words, delta G naught is equal to minus RT ln of K. Now we're solving for K here, because we know what delta G naught is, and we know what the temperature is. And so K is equal to e to the minus delta G naught over RT. And so that gives us e to the minus 8.5. Well, it's kilojoules, so I'm going to convert this to joules. 8,500 joules. That's our delta G naught. Divided by R, 8.3145 joules per Kelvin. And T, which is 298 Kelvin. So this comes out to 0.0323. Well, this is equal to K, and K is equal to the partial pressure of H2O gas. It's the activity of the products over the activity of reactants. And so the partial pressure of H2O gas must equal 0.0323 atmospheres, or bar. Actually, is this atmospheres or bar? Bar. A bar and an atmosphere are about the same. Really. About the same. That could account for the earlier error. The earlier, we know the normal boiling point of water. The normal boiling point of water is the temperature at which the vapor pressure is equal to 1 atmosphere. An atmosphere and bar are slightly different. So I need to double check. And so this is what we have to do. In order to boil water, RT, we have to go non-standard. So under standard conditions, the water normally has a pressure, we call P external, of 1 atmosphere. So there's 1 atmosphere of air pushing down on the surface of the water. We aren't going to see any boiling until the vapor pressure matches that. And so if we have a vapor pressure that's 0.0323 bar, then we need the external pressure to match that, and then we'll have that spontaneous boiling. This is going to be 0.0323 bar. The way to go from about 1 bar, which is the normal atmospheric pressure, to 0.0323 bar is by hooking this up to a vacuum. And so we suck out the air out of here to create a vacuum, and once the vacuum hits 0.0323, then the water will start to boil spontaneously. H2O liquid goes to H2O gas under non-standard conditions, that is at a pressure of 0.0323 bar. What I mean by 0.0323 bar, if there's 1 bar of pressure out here, then in the vacuum we have to create 0.03 bar. And there's a huge pressure difference, so then the air from out here is being sucked into here, right? This is what the vacuum pump is doing. What do you think? If there's 1 bar out here and I put my thumb here and this was 0.03 bar, do you know what would happen? It would probably suck a chunk of my flesh into the vacuum, but it didn't. This vacuum is extremely weak. And I tried it. I tried to boil water with our house vacuum. It didn't work. That was my demo, and that was a failure. And so our vacuum is too weak. We need a stronger vacuum. You have to watch out for that because, sometimes these things aren't achievable. Like sometimes you do this calculation and you come up with a pressure of minus 0.4 bar. Is minus 0.4 bar achievable? No, minus 0.4 bar is like asking somebody to cool something down to minus 200 Kelvin. Is minus 200 Kelvin achievable? No, it's impossible. Because the lowest pressure we can have is 0 bar. Absolute pressure. But there are 2 types of pressures though. Do you remember gauge pressure and absolute pressure? You could have negative gauge pressures, but negative gauge pressures aren't really negative pressures. They're just lower than 1 atmosphere. And so certain pressures are impossible. This is impossible pressure. Or certain pressures aren't achievable with our technology. The chemistry technology, this is not an achievable pressure because we don't have a vacuum pump that's strong enough to pump down that hard. In physics, they do. So if you're taking physics, they can boil water at room temperature. Or if you go on YouTube, lots of people do. And we're trying to get a vacuum pump that's strong enough. But we haven't gotten it yet. And so what we have to do is we have to make do with the vacuum that we have. Now, what would you estimate the vacuum is here? If the external is 1 bar, then the vacuum here is less. Maybe it's being sucked in there. Maybe. What do you think the pressure differential is? Half a bar? No, I think if it's 1 bar out here, it's more like 0.9 bar in here. Very weak vacuum. I think your household vacuum is stronger than our house vacuum here. If you have a vacuum for vacuuming your carpet, if you have carpet, this is a very weak vacuum. But we'll be generous and we'll call it a half a bar. Let's say all we can achieve is a half a bar, but I still want my water to boil. If I want my water to boil, I only have a half a bar here. Do I have to heat it all the way up to 300? No. And so what I could do is I could do a combination of things. If our vacuum pump is only good for 0.5 bar vacuum, then what temperature do I need? So is this under standard conditions or non-standard?
No.
Non-standard. And so I'll just do this. Delta G is equal to delta G naught under standard conditions plus RT ln of Q. And again, what I want to do is I want to go from non-spontaneous, that is a positive delta G, through 0 to a negative delta G. So, you know, the borderline is going to be 0. So I'll set delta G equal to 0, which is equal to delta G naught plus RT ln of Q. And then solve this equation for T. That is, T is equal to subtract the delta G. So this is going to be minus delta G naught over R ln. When this is 0, then Q goes to K. So this is ln of K. And so I know what my delta G naught is. What is my delta G naught? 8.5 kilojoules under standard conditions, right? And so it's a minus a plus 8.5. R, I know what that is, 8.3145 joules per Kelvin, so I'll have to work out the units. ln of K, what is K? In this case, K is my partial pressure of H2O gas, which is 0.5. You know, because I want the partial pressure to equal the external pressure generated by the vacuum pump so that water can boil spontaneously. And then solve for my temperature. And what does my temperature come out to? Well, we need to convert this to joules. So let's go minus 8,500 joules, or 8.3145 joules per Kelvin, ln 0.5.
1,474.
1,474 Kelvin. So if I have a little bit of vacuum helping, then I just need to heat it to 1,000 Kelvin, 474 Kelvin. Does that sound right? No. If there's a little bit of vacuum, it should be easier, right? I don't have to heat it as high because I don't need to generate as high of a partial pressure. So there's something wrong here. Can somebody tell me what I did wrong? Looks like everything's okay. Uh-huh.
Is it because of where you're getting the delta G from when it's at 298 Kelvin then?
Yeah. That's it. This is not round-off error. This is a major error. The major error is this. This temperature, can I just safely assume that my delta G naught at 298 Kelvin is the same as my delta G naught at this temperature? No, because what happens with delta G is it changes dramatically with temperature, as we saw before. And so delta G, this is at 298 Kelvin. This was the problem here. I needed my delta G at this temperature, whatever temperature that is, not the delta G at 298 Kelvin. Does that make sense? So all I need to do is I need my delta G at the temperature, but the problem is I don't know what the temperature is.
Can we like graph and find the equation for it?
Yeah. We could try that, but it turns out we don't have to do that. We don't have to do that because we could get delta G naught in terms of this. Delta G naught at temperature T is equal to delta H naught at temperature T minus T delta S naught at temperature T. And so if we do delta G naught at temperature T is approximately equal to delta H naught at 298 Kelvin minus T delta S naught at 298 Kelvin, then this works. And so what we're going to assume is this. We're going to assume that the delta H's and delta S's don't change much. We can't make the same assumption about delta G, though. Delta G does change significantly with temperature. And so this equation is wrong. In other words, we have two choices. We could rearrange this equation, that is T is equal to minus delta H naught at 298 minus T delta S naught at 298 divided by R ln of K. And then we have to get T together. Solve for T. Or back up. I'd like to back up and solve this for T. And so let's back up a little bit. If we back up, we go here. The delta G is equal to delta G naught plus RT ln of Q. We want this equal to 0, so delta G is equal to 0, which is equal to delta G naught plus RT ln of K. Then we'll substitute it in here. Delta G naught at temperature T, right, is equal to, approximately equal to, delta H naught at 298. We're just saying, right, approximately. Minus T delta S naught at 298 plus RT ln of K. So let's get T's on one side. So we get T delta S naught minus RT ln of K. So we'll put the T's on terms on the left. Delta H naught at 298 Kelvin. Delta S naught at 298 Kelvin. Really, these should be at temperature T, but we don't know what temperature T is. And then we're going to factor out the T. So T is equal to delta H naught at about 298 Kelvin. I'm going to say approximately equal. Divided by delta S naught minus R ln of K. And so we just calculated the 298 Kelvin values. Delta H naught at 298 Kelvin was plus 44 kilojoules, or 44,000 joules. Delta S naught at 298 was 18.89 joules per Kelvin. R, 8.3145 joules per Kelvin. And then ln of K. K, we only have a half atmosphere vacuum. And so we get this. All right, so now let's solve for T. So this is better. By having a little bit of vacuum help us, we don't have to heat the water to as high a temperature. And so under this pressure, water boils at 352 Kelvin rather than 370 Kelvin. This is a concept of high altitude cooking. High altitude cooking, the pressure is lowered. Water boils at lower temperature. Also, vacuum ovens. I used to use this one, the Lindbergh vacuum oven. A vacuum oven is just a very sturdy oven, so it doesn't implode. What you do is you have a vacuum chamber here, you hook up a vacuum pump, and then you can dry things at a much lower temperature. Normally you'd have to heat it to pretty high temperature to dry off all the water, but with a vacuum oven you can go way lower. And that's advantageous when you have products that are heat sensitive. A lot of organics, you don't want to heat them too high a temperature because they'll start to combust, right? They'll become oxidized. And so you've got to be careful with those. This is a vacuum oven. All right, let's take a look at another example problem from this chapter. Let's finish one of the problems we started a while ago. That problem was this one. Combustion of nitrogen. Did we look at this? Nitrogen plus oxygen? Did we calculate I thought we calculated the delta G for that. Number 77. Nitrogen plus oxygen gas yields 2NO gas. Did we calculate the delta G under standard conditions for that? No. No. All right, let's go ahead and calculate the delta G under standard conditions for this. What's the easiest way to calculate delta G? From the delta G's of formation. And so let's go look for the delta G of formation for NO, the product. It'll be under nitrogen. It would be the second one. And so 8655. So we got 2 moles of NO. So this is just 2 times 86.55 kilojoules. Right? That's the product. Minus the reactants. Well, what is delta G of formation of nitrogen? N2. 0. Because we're forming N2 from N2. And the same thing. What is delta G of formation of oxygen? And so this is 0 plus 0. And so this is just 2 times 86.55, which would be 160, 172, 173, plus 173.1. Is that right?
Yep.
Okay. Plus 173.1. Well, that's quite a bit different than the last example. The last example was plus 8.5. This is a plus 173. And so let's see what the magnitude of delta G, what kind of information we get from that. And so we'll see delta G and K equilibrium. Find the page. Okay, here it is. So if we have a delta G of 173, what does that tell us? It gives us some information. And so the delta G numbers that you want to remember are this. People typically remember between plus 50 and minus 50. Between plus 50 and minus 50, we have an equilibrium. That is, we have significant quantities of both product and reactants. Above plus 50, it becomes more and more reactants. In fact, at plus 50, we have a K, an equilibrium constant of 10 to the minus 9. Remember the cutoffs for Ks? Ks, we were looking at 10 to the positive 10 to the 10 to the minus 10. Between 10 to the positive 10 and 10 to the minus 10, we should do equilibrium calculations because significant quantities of both occur. And so at plus 50 and minus 50, this is going from about 10 to the negative 10 to 10 to the positive 10. So here, equilibrium calculation is necessary. Above plus 50, it's all what? All reactants. If you have an equilibrium constant of 10 to the minus 36, is there very much product in that equilibrium? No. And so normally in Chem 1A, we'd say it's no reaction. And then look down here, below minus 50, like minus 100, minus 200, we're going from 10 to the 35. 10 to the positive 35, is there very much reactant? No. This is all product. And so in other words, we have no reaction, complete reaction, equilibrium mixture. And so the equilibrium mixture is between plus and minus 50, essentially. That's for general qualitative prediction. But the problem is I say this, and then some people will say, oh, delta G is plus 100, I don't need to do a calculation. Well, if the delta G is plus 100, I want you to do a calculation. So I don't like this table because in Chem 1B, an equilibrium calculation is necessary for all of these. In Chem 1A, if you go back and flip through the chapters and you look at stoichiometry, we did stoichiometry on reactions that essentially go to completion. Well, in Chem 1A, you aren't going to select a reaction, that has a delta G above negative 50 for stoichiometry. And so in Chem 1A, the types of reactions were limited. In Chem 1B, we wanted to do any kind of reaction, and therefore we wanted to do calculations for any of these. And so you just remember plus 50 and minus 50 is just a general guide, but not necessarily where you have to do calculations and where you don't have to do calculations. We're going to be doing calculations for everything. And so what this says is this mixture, is this spontaneous? No, it's highly non-spontaneous, which is a good thing because air consists of nitrogen and oxygen, and NO is toxic. And so NO is also called NOx, which is a pollutant form. NO is quickly converted into NO2 by air. But NO has important biomessenger properties. Anyway, this is highly non-spontaneous. Can we make this spontaneous?
Yeah.
Maybe. We have to, before we say that, we have to look, we have to look at delta H and delta S and see if it's one of those scenarios where we can change the temperature and make it happen. Well, it turns out this is one of those scenarios where we can change the temperature and see what happens, but we need to know what the delta H value is and the delta S value is. So we'll calculate those. I was planning to finish chapter 19 today, but it looks like I'm going to have to finish it on Wednesday, which means the test will be on Thursday. All right. All right. So let's stop it.
And we have last time.